Okay, so we have done slicer. We have done those things from array to slicer, and we left this part. Today we'll today we will cover this part, those parts: mutable slicer, to state, index straight, and index mute hash map, and battery map. These two topic is too important for us because um, they use most most of the place they used. So deep dissect, we will take help, right, of AI, because this is the AI race, and we should use all the goodwill of AI, right? So there is no big deal when we use AI, but we have to understand the core concept, right? So let's start today's topic, that is mutable slicer. Okay, in short, a view that allow modify the element. That means mutable slicer is a slicer that is that can be mute, like this. This is a mutable slicer. So we will, okay, let's see mutable slicer. Okay, here you can see this is the slicer, this is the slicer sheriff, and this is mutable, right? We can change the number inside the vector. That is the mutable slicer, but we are learning deeply and from the docs, right? So that's why we should jump into the docs, because there is lots of specific things we have to understand about mutable slicer, right? Because docs are more docs are used to have a lot more information, right? So you can see the mutable slicer here. They are saying that every time we have talk about slice type, like str and generic t, this is slicer, we use the immutable borrowed. That means maximum time we use immutable slicer, right? This is the uh, immutable slicer, and this is the immutable slicer. So what is going on? But slicer can be also immutable. The fact is slicer can be also immutable. Here we can see this is the slicer, and this is immutable. You can see this is immutable, and we can push, we can modify the slicer like this. In zero index we can push 42, right? Okay, right. So the limitation of this when working with mutable borrow, the recommendation was clear: prefer slicer reference over the reference to own type, right? That means when we use immutable borrow, the recommendation was clean because we pass reference, right? Here is the reference, we pass reference of slice, reference of backed. Okay, here you can see the scenario, right? what we can understand by that is here here is a vector with the capacity of 2 and mutable number okay. So what we can understand that is let mutable slicer. What we are saying that we can push in the slicer by mute it, right? So they are saying it won't compile, so we should we should duplicate it and yes, just what we are doing, that is we will check why that will not compile. They are saying it won't compile. Push is a method on vector, not a slicer. So this is vector, right? But they are saying that it is work in vector, not in slicer. This is the main manifestation of more general principle. Rust won't allow you to add or remove element from slicer, right? You will only able to modify, replace the element that already there. That means I can only modify and replace the element is already there, right? So in this we want to know what is going on in this. So we do one and 1 2 and OW set what is GUI on in this, right? Okay, let's see what is going on in this part. So here they are saying it won't compile, so it is a big deal for me because I don't know why that will not compile. What is the compiler error? Let's see. Okay, right. So the compiler error saying that method on found in mutable slicer. So the method is not found in the mutable slicer, right? Now here the answer we found from the AI. The compiler won't work. Don't push the method. Let's work to what happened. Let's see what happened. Vector with capacity to create an empty vector I32 with enough allocation memory to store 2 element without reallocate, but its length is still 0, right? Why? There is no element yet, right? We are creating empty vector, allocating the memory, store 2 element without allocating, but its length is still 0. There are no element yet. So let mute I32 mute number, right? So what is going on? The Rust perform differ what is going on? We should understand that
here Rust performs deref coercion.
Coercion, that means let mute slicer clone mutable slicer mute number. So we are having a vector that is mutable, right? The rest is perform derefer cohesion. That mutable number is a mutable vector, right? So mutable vector implement deref mute target. Okay, so mutable can be a sorry, let me check. Okay, that means forcefully, right? Can be forcefully into mute I32, right? The result is mutable slice that views the vector underlying buffer. So slice is not a vector. Slice is not a vector. It is mutable reference, right? Mutable slice reference. That is why the next line failed. Do you understand what is going on? Okay, I should copy this part, because here we have to know lots of things, right? Okay, right, this is the mutable slice. This is the mutable slice. Okay, great. Okay. Right, so shit. Control A. Okay. Right. Okay, so that is what we found, right? Okay, so this is mutable slice, mut slice, slice, right? The topic is mutable slice. And what is going on here, that is in this line here you can see let's check. Oh shit. Okay. Shit. Control back, right? Okay. Middle number is mute vector I32. So right, so here we can see what is going on. That is, we now I what I understand, I will explain to you. That is, this is the vector, right? So when we take this vector in this part as a mutable vector, right? This is mutable and this is the mutable vector, but it is pushed into a slicer, right? So that means from vector it become it came into the slicer. That means the type has changed, and it was vector but now it was a slicer. So the main fact is we can't use sorry, Okay, the main factor is we can't use push on slicer, right? Because we are forcefully pushing the vector into this slicer part. So that is the main core thing, right? If we that is why this code is not working. And if we want to work this code, what can we do? We have to delete the middle point, or we have to change the orientation, right? Because copy. Okay, wait. um, hmm, um, okay, now if we run this, what will it will compile, right? Okay, not found in the scope. Slicer dot push. Okay, sorry, slice is not found in the, we have to push in the number. MBR numbers. Now it will compile. Okay, it compiled, right? Okay, that means what is going on in this part, that is, oh shit. Okay. Right. Okay, we can understand the background. Shit. So we have to, we will change the color and send it back. Okay, so this is the code we just saw. And yeah, you can use this, this obsidian, right? It will make you more understandable, and you can visualize the code, what is going on. So now you can understand why this is not working, why this code is not working. And we complete all of this section. And if we capture or overview all the topic what we learn from this section, so they are saying that reference, slicer can be mutable. We can use this mutable slicer, and if we want then we can just use the type by this way. And we have to understand the limitation also when we do this type of thing. That is, normally immutable slicer is a reference, that is not in the case of mutable slicer, right? So in mutable slicer, so why this code is running, you can, in my head something is coming, like some one question is just arrived, that why this code is working. Okay, if this code is compiled, then that means everything's okay. What is going on? We just have three element, and in the index 1 we just pushed a number, but in here we have two capacity. We just uh, to create a space in memory for two things, and we want to, here this part is not working, right? So and here you can see we just create a memory space, and in the vector we change the type, right? So here you can see if we add slicer dot push, what will happen to this? Let's see. Okay, this is compiling. Okay, that means if we specifically said that push if we specifically said that you can push this, then it will work, right? But if we want to use vector method on this, that won't work, right? So that is the main fact we understand from this, that means after changing type, so okay, after the type change it, after the type change, it become become, after the type change it so you can't use any MATSO, the method of PIOU previous TIPYPE type. What we are saying, we will show here after the type change. Here is the after the type change, here is the type change, and any method of previous type, this is the previous type, right? So sorry, okay, okay, right. So this is what we are saying, that after the type change, it can be used any method of previous type, right? So this is the fact we have to understand, that okay, find. Now we almost complete this this part. We almost complete this part. So here you can see, okay, this part is end, and now we will have part 2. What we have in part 2? The two state. Okay, two state means what we mean by two state. Let's see. Okay, right, right. So to state, so at first we will see the title what is to state, then we will dive into the to state. So in mutable slicer, that means we can use mutable slice to change the slicer items value parameter, right? So but but on the other hand, if we see, so if we understand that the mutable slice have, we can change the slice, that is the fact, but we can't use the previous, let's say this part, we can't use the previous type type what we can say, um, this is the vector, right? So we can't use the vector types, the vector method implement here, because the type has been changed, right? And the type has been slicer, right? So that is the fact we just learned from mutable slice. This is the in advantage. So let's jump into the next part. We have to state part. The to state part, what they are saying, that borrowing rules, share versus mutability, you can have many reader or one writer, right? But not both simultaneously. That means I can read like everything, I can read from the code bases. Let's say I have 1000 line code, and I can read every code or every variable in the code, right? But I can only write one code. What it means, let's check this out. So I understand this part, but I will go to, okay, I understand this part, but I will go through this. Okay, this is the mutable state to mutable state, yeah. This is the type, okay, right. So so I found that the tricks, and okay, so we will see what, at first I should explain what is going on. That means, let's say we have okay, right, let's say we have here, okay, we have 5 variable. Let's say we have 5 variable, var1 equals to 50, var1 equals to 50, var2, var3, var4, okay, var2 var3, var4, 33, 68, say 55, okay. We have 4 Okay, so let's say we have these 4 variable, right? Now let's assume we have, oh shit, let's assume that we have different program running in our machine. Let's say this is program 1, gram program, a program a, okay, program a, program b, program c, program d, program f, okay, b, program c, program d, program f, right? So we have 5 program, right? Now we will the program, one program can read one variable can read by multiple program. Sorry, I have an issue, that is okay. So here you can see one program can read one variable can read multiple program. So here we will, sorry, read and read only, okay, read only, right? So read only, right? So let's see, okay, sorry, I think I should use, okay, read only, right? Read only. So this is read only, right? So the variable is can be read by multiple program, but it can't write by multiple program. Now we will see, we will write so okay, so we have one write only, w write write alloy, okay, sorry, write only. So we can only write one variable, that means we can change this variable by this program, but we can use multiple, ঠিক আছে। So here you can see that we can use one variable in multiple, we can read multiple program, but we can't use one variable. We can't write in multiple programs, right? We can write only one program. That is the fact. That is factually correct. Hmm. Okay. 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 So write only. So we can understand that write only, read only. Okay. So this is the core concept of two state two state in Rust, but we will go through the docs. What the docs are just saying that um, let think again about our ticket management. Okay, we have a ticket management system. On this thing is missing here an identifier or uniquely identify a ticket, so that defined should be um unique for each ticket that can be guaranteed by generating it automatically when a new ticket is created. So the referring the model here, we will see what is just change. We should when the where should the id be stored. Okay, we could add new field to the ticket structure. This is previous structure, and we have ordinary things like ticket id, title, description, status, but we don't know the id before creating the ticket, right? So it can be there for the get get go. It didn't have to be optional. That means this id should optional, right? That means whether id will be there or not. There is also no ideal. We have to handle the non case every single time. Retrieve a ticket from the store every even though we know that the id should always be there once the ticket has been created. Once the ticket has been created, the best solution is to have two different ticket state. Okay, represent by two separate type. One is a ticket draft, another is uh, let's say sorry for inconvenience. So here what is going on, that is we are just divide this part into two different type. One is draft and one is ticket. So now the question should, why these two? I have that question because I don't know what is going on. A ticket draft is a ticket that hasn't created yet. It does not have an ID, and it does not have an status. A ticket is a ticket that has been created. It has an ID and status. So since each field, ticket draft and ticket embedded each okay, embedded into own constraint, we don't have to duplicate logic across two type. So what is going on in this part, that is, if we want to initialize a ticket, we can use ticket draft. But if we want to create a ticket, there will be ID and status, and we can use ticket structure, right? But I am not clear what they are saying. Let's check in the exercise, right? So what is what we have in the exercise? So here we have a ticket store from the ID. Okay, so we have ticket draft. So you can see here that ticket store, we have ticket store structure, and we have ticket ID, right? And we will use this ticket ID on this structure, ticket ID, right? We are using this structure on ticket structure, right? But here you can see we have two structure. One is diff ticket draft and another is ticket, and one have ID and status, another don't. And we are implementing at ticket ticket. So we are using the ticket. Okay, we are using this ticket, right? Right. Okay. Ticket store. So yes, we are using this ticket structure, but I think right. So the core concept is where we use ticket draft, right? Where we use this ticket draft structure. Let's ticket store. Okay, so this is the ticket store we are using and we are implementing, and it is a vector. It is a vector, and it have ticket structure inside it. Okay, but where we use ticket draft? Okay, yeah, if we want to have okay, that means if we want to create a ticket draft, then we can easily create the draft, right? But on the other hand, if we want to create a ticket, no draft, no nothing needed, and we direct create an ticket with ID and status, right? So this is what is going on inside the code. And a ticket is a track has been created, an ID and status. So refining the model. So we are refining the model. What we understand that um, sta- state. So they are saying that two state we are using. um, Best solution is two different state represent by two separate type. So the core concept is also no idea. We have to handle the unknown in case every single time we retrieve an ticket from the store, even though we know that the ID should always be there once the ticket has been created. Okay, that means we have to check every time that the ID, but we know that after created one after created one ticket, um, always there will be ID, right? The best solution is to have two different ticket state represent by separate type A, ticket draft and a ticket, right? Okay, so a ticket draft is a ticket that hasn't been created yet. It does not have any ID and it does not have status. The a ticket is a ticket that has been created. It has an ID and status. Since each field in ticket draft and ticket embed its own constraint, we don't have the duplicate logic error across two different types. Okay, that means we have no duplicacy, and for handling we just using this structure for handle the data easily and remove the constraint, right? That's why we are using two state. Okay, I understand that. So here is the indexing, most important topic in Rust, that is an indexing. So we know that a vector have index, right? So what is in this document, we will deep dive now. We all know this, right? But we don't know the deep meaning or deep depth of indexing, right? We will read Rust indexing now. So ticket store get return an option ticket, right, to give a ticket ID. Okay, we see before how access element array vector using Rust indexing syntax, right? So um, so the vector, what we can see here, how can we provide the same experience to ticket store? Here you can see we are checking that in the index 1 there will be value 0. We are saying that in the index 1 there will be value 0, and we are checking this, and this match with our vector, right? How we can prove on the same experience for the ticket store? You guessed right, we need to implement a thread index. Okay, the index thread is defined in Rust standard. Okay, so index thread is defined in Rust standard library. Slightly simplified public thread index. Okay, what we are doing, we are using public thread index id index thread. This is index thread means the use case or the uh, core, um, uh, let's say, um, if we can understand the what is index and what is thread, that means if we have that type of um, rules, right? Thread means the rules, the index rules. So what is going on, we are using a type output, that is output, and require method index, uh, function index, self index, okay, self output. So here, yeah, we can see function index, index x, so self output. So function index, index function index self index id, index id self output. It has the generic parameter idx to represent the index type on associate type output to represent the type we retrieve using the index. Represent the type, associate type output to represent the type we retrieved using the index. Okay. Notice how the index model does not return an option. The assumption is that index will panic if you try to access an element that is not there, as it happened for array and vector indexing. Okay, so I am confused with this part, so let's check in AI what they are saying, and I will ask AI explain this topic, right? Xpla and explain this topic topics. So what we found here, the index thread in Rust allow you to use a square bracket syntax. On your own types, exactly like you do with array and vector. It part of the standard library and it is defined as okay. So the index thread in Rust allow you to use the square bracket syntax, container index on your own type, exactly like you do with the array and vector. It is part of the standard library and is defined. Okay, and is defined, right? So is generic parameter. Index is generic parameter. Okay, we know that is in generic parameter, and output is associate type. The type of value return index I32. Okay, for the vector I32. So, and or ticket or a store, that means output can be any type, right? The index method return the reference self output, not a an option. This is important. By design, index assume that element exist and will panic if don't do not. It's like vector 0, vector 10, and on vector C with 3 element panic. Okay. Why implement index for ticket store? Your ticket store currently has a get method safely returned option ticket. This is great for sellers who want to handle missing ticket gracefully. However, sometimes a ticket should be present and you want to um, um, conscious about direct access that index provide. So what we understand that your ticket currently has get method that is safely return option. That is great call who want to handle missing ticket gracefully. Okay, however, sometimes ticket should be present and you have to I have to concise direct access that index provide, right? So what we are doing here, we have a ticket store new ticket, and it store insert the id is 1 and the new ticket, and the ticket store get id is unwrapped, and inside of the ticket we can write the ticket store ticket id. Okay. There is ergonomic and familiar to Rust developer because array and vector already work this way. How to implement index for ticket store Okay, how to implement index for ticket store? Let's assume ticket store initial use hashmap ticket id ticket to store ticket. We can implement index ticket id like this. Okay. Type output ticket tells Rust index return a ticket self dot ticket id work because hash items implement index k and it panic if the key is absent, so we get the same panic before the free. Okay. So the more or less point is index cannot be returned option, and only immutable index is defined as indexing is defined as index. So returning reference require value stored somewhere stable in heap hash map. So yeah, I just understand that we should skip this part because I think this is not important. Mutable indexing. Okay, that means we can change the index number and it is not important, that's why this part is too small. And you can see this is the index, and it is mutable, right? It is mutable. Okay, now we will go to next part, hash map. So what I am just waiting for, that is the hash map. So hash map is the most important topic from this uh, whole set, right? In this whole set we have most important topic, that is hash map and byte tree map. So we will learn this, and you will find lots of important um, information from this video, right? So hash map, right? Our implementation of index uh, mute is not ideal. We need to iterate over entire vector to retrieve a ticket by id. The algorithm complexity is 0, and that is too high, where n is the number of the ticket store. That means this is not feasible for real life work, right? Now we can do better using different data structures store ticket in hash map. So you can see two things on this hash map. One is key, k means key, and v means value. So one is key, another is value, right? So what is going on, we are using hash map, and hash map is a collection. So what we are doing, we are initialize a new hash map that is called book review, and we are insert two string on the book reviews, right? Hash map work with key value pair. It generics over both. K is a generic parameter for the key type, where v is the one of the value type. So expected cost of insert, retrieve and remove, its constraint 0 1. Sound perfect for our use case, doesn't it, right? In that sounds perfect for our use case, doesn't it? That means we will have time complexity of 0 1 because we have key and because we have value, right? So now this is the most important structure, because if we understand this structure, then we can use lots of place. Like now I will show one example. SD. Okay, why I am here? You can see this is hash map. Now I will paste the hash map. Okay, here you can see all the method in hash map, and all the trait implementation in hash map, and auto implementation in hash map, bracket implementation in hash map, and the collection, that is collection module that is in the hash map. And so that means okay, so you can search from this place, and you can use these functions. Now you can say insert function. We can use insert function where that there will be key and there will be value and it will return a option. So that is the insert, right? And we can get use get function. There will be key and it will be return a reference of value, right? So here you can see the this part. You have to understand this part. That means what we are supporting here. We will support equals and hash and size in this function. So that is why we have to understand this structure perfectly, right? So let's what is going on. Let's see. There will no trait bound. That means there is no trait connected to this hash map structure definition, but you will find some on its method. Let's look at insert. For example, let's see what is going on inside. So here is the impl and the hash map key and value, where key is equal plus hash. Okay, and we are using insert function, right? So we have to understand this part. Now I will go in DeepSeek and search what when we use this right. Okay, when we use this where key a clone equals hash, when we use this part we have to understand, else we will never understand why when we are using this is cause. Okay, where k is equal plus hash, cause in the snippet is a trait bound, right? It is a trait bound. That means if we implement this hash map, there will there I have to implement the equals and hash also. That these two things are the bound, right? So what is going on? Hash map, hash is a trait and we are bounding this equals and hash. That's why it is trait bound. It tells Rust that insert method or the whole implementation block is only available to hash map. Okay, instance where the key type k implements both equals and hash trait, right? Okay. The key implements both the key and hash trait. Key implement both the key and the key implementation both the key, where the key type k implements both the equals and hash trait. Equals and hash trait. Where the key type k implements okay, where the key type k implements both the equals and hash trait. why does the hash map insert need on those boundary? Okay, there we are saying that in the hash map key and value instance, where um, in the instance key name equals and hash we try to implement. Okay, so and both are both the equal and hash treat. That means k implement, k is the key, implement equals and hash treat. That means we can use the key, and now I can describe, I understand that what it means, right? So this is the okay. Okay, so no, we are the key will use as a equal e q q u a l equals, we use as a equals, key use as a equals, key will use a key will use to check the id that is y equals eq use, that is why eq trad trait, and I am to implement okay, the key okay, and the key will use to check the id, that is why equals state are implemented. Do you understand what I just say? And it is also hash, that means without key plus equals plus hash, we it would be impossible to guarantee the correct behavior of the math, because there would no way to hash the key or check it to key as the same or not, right? So okay, this is what we just said, right? Okay, so here okay, you can see this is what is going on, in the hash map. So the core, sorry, the byte map, sorry. Okay, so the core concept is that is we will use we will use this structure on our okay, right. So okay, let's check it. Sorry. Okay. Okay. Let's check. Okay. Let's see. Where's no, not at all. Okay, right. Day by day. Okay. Okay, so you already know this, and that why we use hash. We use hash to hash function will behave in the hash. You key it has the key, so we it will just hash our key for safety and security, right? And in equal trade, I just already said that we can use this equal sign for equal trade, right? That's why we implement that equal trade. So it is market trade. It does not add any new method. It is just way for me to stay in the compiler that stay to the compiler that the equals logic implement in part particular equals is reflexive. So you can drive equals automatically where you drive partitional equals, right? That means we can use this partitional equals in the structure, and we can use anywhere. So the equals and hash are linked. It is an impact impractical contract between equals and hash, that if two key are equals, then the hash must be equals to the key. Okay, that is mm, 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 okay. Okay. Oh, sorry. Control G, right? So okay, so okay, Okay, so we have done this this hash function part. So that means we almost cover the module 6, and we have only left byte tree map, and it is also an important, and we will first see what is the difference between hash function and byte tree map, right? Let's build. Okay. Okay. Ordering. Okay, by moving from vector to hash map, we have improved the performance of our ticket management system and simplified our code in the process. It is not all rows through when iterating over a vector. Okay, we are moving to vector to hash map. Okay, we have improved the performance. All right, the ticket management system simplify our code process. Okay, understand that it is not all roses. Okay, iterate over vector backstore. We could be sure that the ticket would be returned an order they were added. That means okay, there is not the case with the hash map. Okay, the factor is okay. Why? First we have to understand why byte tree map came, right? So first we have to understand yeah, why byte tree, sorry. So why byte tree map is why byte tree map came in this WRL world. So this is the core question, right? Why byte tree map came in this world? Right. Okay, so the answer, okay, yeah, nice answer. Okay, so why byte tree map came into this world? Answer is uh, vector. We see vector have say we have index number, but as a hash have don't index number, sequential index number, sequential, sequential, sorry. Okay, I think okay, I have to check all sequence vector have sequential index number, but hashmap hashmap didn't. But hashmap didn't Mhm. Have a sequential index number, but the hash map did not. Mm. But hash map didn't. Okay. Okay. So the fact is sequential index number, but the hash map didn't. Um. hmm, uh, Vector has sequential index number, but hash map didn't, right? Hmm. That I have to justify this word. I have to check this line because it is from myself. Let's check this line to by the AI. Okay. Sequential number hash map didn't. Okay. Has sequential index number, but hash map didn't. So AI has been stuck. I have to search in Gemini, right? So what I just understand, vector has sequential index number, but hash map don't have this. We can recover constant ordering by switching from hash map to binary map. This is the fact. The party. Okay. Yes, the between the memory. Okay. But under level. Okay. Have request my index. No sequential index, right? So the fact is okay. So the difference is exactly what we use program. Okay. So the sequence when we pass the key, system has take key to into pseudo random integer, map that integer to a bucket, and then resolve collision. It is not sequential, mathematically complex, and require dynamic heap expansion. So here is the core thing. If we want to when the pass the key system the to reckon then the result collision, it is not mathematically complex. Okay. Okay, this is the core into okay, this is the core thing. Okay. 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 So let's see what happened. Okay, when we pass a key, the system has that key into that key. Okay, that key into a pseudo random integer, map that integer to a bracket and then solve the collision. It is non-sequential, mathematically complex and require dynamic heap expansion. That is the core problem, right? That is the core problem. Okay. Okay, that is the core problem, right? Okay. Okay, that is the core problem we face in hash map. That is why bit3 map came out. That means bit3 map guarantee that entire entry are sorted by the key, their key. It is useful when you need iterate over entire specific order, or if you need to perform a range query. Okay, like hash map, you won't find that bound define bit3 map, but you will find trade bound method like order. So we have inbuilt order. That means our key is sequentially key index it sequentially, right? So if we ask what is the okay, place order, we will have place order trait. So if we ask that what is the then was what is the and between p versus ve vect, right? Okay, so the difference between bit3 map and vector is reference to enter difference relation between CPU caching and memory allocate. If you don't understand physical layout, the structure will be deploy inefficient index protocol. Right here is the structure trade down the memory layout execution difference. Okay, in the vector we flat memory layout is flat and contiguous, meaning one by one. That means one by one, right? But in the bit3 map memory layout, a root node contain an array of key and pointer branch out to a child node. Every time a node fill up the heap allocate must be provision a new memory block, split the node. Okay. So access pattern hardware level. Okay, hardware advantage. Modern CPU fetch memory cache line while the CPU automatically load the next element into the ultra fast L1 cache. So we use L1 cache in vector, right? And that is fast operation. Search pattern, if you want to find specific ID, that is the problem that need O of n complexity. So the search penalty we have in vector. So sorry, vector v sorry t v is t or vector as a csr as a slash and sorry vector. Okay, it is too big. Okay, right. Search penalty. Right. Okay. VEC vector search penalty. Okay. Right. Vector search penalty. If you want to find a specific user ID in a vector, you must linearly scan every element on O of n time complexity unless the vector is pre-store and the execution and binary search. That is the core penalty. That is why we use this byte tree map. So the core, do you understand the core thing, that why we use byte tree map? So we use byte tree map. Now we will see the advantage, right? Sorry, we will see the advantage. Okay. 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 Advantage, sorry, algorithm advantage of byte tree map. Advantage byte tree map b tree p, right? Okay. The key are mathematically grinded to be sorted. You can iterate through a byte tree map in perfect alphabetically or numerically order, which is impossible with hash map, right? The key are mathematically guaranteed, right? The key are mathematically guaranteed to be sorted, right? You can initiate through a byte tree map and perfect alphabet or numeric order, which is impossible with hash map. So we have also hash map. We have some specific advantage also. So following the pointer across different area, the heap bracket catch locality. CPU cannot perfect the data, prefetch the data, because it does not next node live in the memory until the read the pointer. That means the main fact is after reading then the CPU arrive, but in the vector after reading before reading the already the pointer is available in the memory, right? That is the main core concept. That is the core concept. Okay. And advantage, if we ask for advantage, mathematically guaranteed to be sorted. That means we know already, we saw already sorted. You can iterate through byte tree map it in perfect alphabet or numerical order, which is impossible within hash map. Okay. When we use okay, more or less the main concept we understand from this byte map, that is byte map use to replace hash map, and why hash map don't have sequential indexing. That's why it is too tough to search a product from hash map, right? But on the other hand, byte map have inbuilt order. That means it will order the it will order the value key according to the serial, right? 1 2 3 4 5 6 7. So it will order it, right? So this is the core concept. And if we ask that why I use byte map instead of vector, so this question this answer is given in here. That is vector have search time complexity of search O of big O of n, and byte map have big O of 1. So that means the time complexity is sorry, byte map have okay, time complexity okay, time complexity is log n, that is smaller than this big O of n. So that's why we use byte map. And yeah, this is the core concept of byte map. Why should we use byte map? If we deep dive into this part, we understand why order use. Because of search engine optimization, we use order in byte map. We have two powerful things, that is we can use as like hash map, and byte map is just think it is the mix of vector VC vector and hash map, as a hash map, right? It is the mix of vector and hash map. So yeah, it is so sorry, okay, right. Byte map by t map equals to mix v sorry v 7 or plus hash map is map. So yeah, this is the core concept. And I will give you all the things we just write down here. So you can check in the video description. There you will find the story part, how we learn with story, and the basic description, and code, you will not get the code. If you want the code also, then you have to comment or message me on, and I will provide you the um, file through Google, right? So yeah, that is today's um, topic, today's video, and we cover all those things in three part, 1 to 3. And I think the our next topic will be thread, and we will cover this thread part in next videos, one by one. And those are the core concept of Rust, and we will also implement them in our project. So I am building a project on stablecoin payment system. Okay. SKS okay. Yeah, you can see I am yeah, so I am building this stablecoin payment system. So we will implement all the topics in this place, and hopefully we can understand the topic more easily. Yeah, stay with me. Thank you guys. I am learning Rust, you will also learning Rust. I know that we should connect with we should connect each other, and we can make lots of